So, welcome back. We have been looking at this language OPS5, which is a rule based production system language. We saw that the knowledge base in OPS5 is called the working memory, and it contains a set of working memory elements. And the working memory elements are basically class names with attribute value pairs stored inside them, and rules have a name and they have a left hand side and a right hand side. The left hand side consists of patterns which should match the working memory elements, which means that the constants in the two should match. The class name should be the same, the attribute name should be the same, but in a rule you can have variables or you can have conditions on values and then match is defined. So, let us look at the rules again. The value field in patterns can have variables and Boolean tests. We have said that patterns are in the left hand side of the rule. So, what are the Boolean tests that we can do? We can test for equality, that it is the same type or they are equal essentially. We can say that they are not the same type or not equal, or we can even just say that they are the same type essentially. Then for integers or floating points only, we can do comparison because they are ordered sets. So, we can say that something is less than something or something is greater than something. The value field can have conjunctions. So, this expression here with the curly brackets, then greater than 3.0 and less than 3.5 essentially says that it should be greater than 3.5 and should be less than greater than 3.0 and less than 3.5. Both the conditions must be true, and that is captured by the curly brackets. The other brackets, for example, they stand for OR, and you might say that okay, you can come and see me on Monday or Wednesday or Friday, then that would be expressed as this, which means that if I am seeking an appointment and the day is Monday, it will match this pattern. If the day is Tuesday, it will not match this pattern. If the day is Wednesday, it will again match this pattern, and so on. So, whether it is Monday or Tuesday or Friday, any of them is allowed, and so both OR and are captured. Ordered sets can be compared and equality can be compared. What about the right hand side of the rules? Is a set of actions. So, in the language of OPS5, we do not say consequent, we say actions essentially. So, the actions could be consequence or at least asserting consequence, but we think of them as actions. In logic, first order logic, we say that an implication statement says that if the left hand side is true, then the right hand side is true. In OPS5 like languages, we say if the left hand side is true or it matches, then do what is given to you described in the right hand side. So, the simplest thing you can do is make a new working memory element, that is like adding a consequent, and that is what like doing things in logic essentially, that if the knowledge base has all men are mortal and Socrates is a man, then add to the knowledge base that Socrates is mortal. So, this part is like doing logic, but you can also remove an existing working memory element. Now, in classical logic, it does not make sense to remove things. Classical logic is also called mathematical logic, because it captures the relations between elements in the domain, and those relations they always exist in mathematics at least, that if something is true, then it is always true essentially. Then what is the point of saying that remove it from this thing? But when you are talking about the real world, when you are trying to talk about actions and change and time, then things may be true essentially. So, if you have let us say a block of ice on your table in Chennai, then pretty soon you will find that the block of ice is no longer there on the table. So, things can be true at some time, things can be false at another time. even if you are doing things like planning essentially. So, you are doing you want to plan how to shift your office from one room to another room. So, initially let us say your set of books was in office 1, but after you execute the plan, that thing will not be true, that AI book that I have in my office is no longer there essentially. So, things can change with time, and OPS5 allows you to do that. Essentially, it allows you to retract statements, and in that sense it is often said to be doing non-monotonic reasoning. Non-monotonic in the sense that the set of true statements does not grow monotonically. It may be, some things may be true at some point, some things may be become false later. So, the set of statements may grow, it may shrink, it may grow, it may shrink. So, it is non-monotonic essentially. We will see that non-monotonic reasoning also plays a role in default reasoning, which we will look at later, that you may draw a conclusion at certain point, but when you get to know more about, let us say, that individual, then you may want to retract that conclusion. And so, you might make a conclusion like which is like a default conclusion that for example, if x is the standard example we use in default reasoning is, if Tweety is a bird, then infer that Tweety can fly. But later on, if somebody tells you that Tweety is a penguin, then you may want to retract this thing. And so, non-monotonic logics do that sort of a thing. OPS5 will allow you to do that, because you can delete elements from the working memory. The language has defined something called modify, which is basically equivalent to removing and adding it again with only a small change that is specified in the modify part. So, maybe you want to change only one attribute, then you can use the modify statement that change the marks. Supposing you are adding up the marks of a student, and when you have seen the physics and the chemistry marks, the total is 172. Then you see the maths mark, and then you add it to say now it is 279 or something like that. Not 279, 259, assuming marks are from 100. But there can also be other actions like read, write, load, halt. So, which by load you mean load a file from disk or something like that. So, all kinds of actions are allowed. All actions on the right hand side are assumed to happen concurrently. It is not that the first action happens first and then the second action happens. We assume that all of them are happening at the same time. The values that those actions use will be taken from the values that was extracted when we did the match essentially. So, it does not matter if you do two actions in two different orders, it will not matter. So, here is this ranking example that we were talking about. If the next rank you want to assign is R, whatever it is, and there is a student S. So, remember that these are variables, it will match all the students, this will also match all the students. So, all the students who have some marks and who have rank nil will match with that. But when we put in the second condition that there is no student with marks greater than this student, then this rule will eventually match only one or two students. So, whoever are the few students who have got the highest mark, they will get the highest, meaning highest remaining marks, they will get the rank that we are talking about essentially. Then we could say something like modify 1. So, when we say 1, we mean the first pattern, which means this pattern, which is rank. So, we are saying okay, modify it to whatever it was before and add 1 to it. So, if the rank that we were talking about was 6 at that point, the next time we assign the rank, it is going to be 7. So, we have already incremented that, and you modify 2, which means the student that we were talking about, and you give him the rank that we were about to assign. So, as you can see, the order of these two actions is not going to affect the result. Whatever was the rank that we were going to assign is going to be assigned to the rank, and whatever is the rank for the next student is going to be R plus 1, but this student is not going to get R plus 1 even though this action comes after that. So, in that sense it is not a imperative language. So, that is what it says. If you have found the record with the highest marks, then assign rank R to the student and increment R. we assume that these two actions happen concurrently. Sometimes we write this a little bit differently. Instead of saying modify 1 and modify 2, we can give names to these working memory elements and then use those names to say that okay, change that working memory element essentially. That of course, will give you the flexibility that if you are changing your rules a little bit, you are adding some other pattern or something like that, then you do not have to keep track of those static orderings that you had said, this is the first pattern, this is the second pattern and so on. You can say okay, this pattern which talked about the rank, this pattern which talked about the total, and even if you shuffle them around later, your program would still work correctly. So, let us look at this program called sorting. So, I am sure you have studied sorting and you have studied various algorithms for sorting. Here we are going to study or look at a program which is possibly the tiniest program you can write for sorting. So, let us say we have an array which is a set of working memory elements whose class name is array and which has got two attributes, one is the index and the other is the value. The objective is to sort the values, let us say in increasing order. So, the first index should have the smallest value, the second index should have the next smallest value and so on and so forth. So, we want them in increasing order. This rule, it spots some two values which are out of place and swaps them essentially. Which two values? We are not saying. It is saying that this will match two records. So, record 1 and record 2. I am just calling them 1 and 2, or maybe I should call it I and j. In fact, that is what it is. Index is I and index is j here. It will look at two records, one which has index I can be anything, it is a variable. J is also anything, but it must be greater than I. So, it comes later essentially. So, if there are two such records such that the first record has a value x and the second record has a value y, but this value is less than x. So, it comes later, but its value is smaller. So, we would like to swap the value and that is what this rule does. It says modify 1 so that its value is y, which is the smaller of the two values, remember y is smaller than x, and modify 2 so that its value is x. So, we have swapped those two values and that is the entire program for sorting an array. The program is tiny, its execution may not be tiny, which is why when we write programs in other languages, we look at things like merge sort and quick sort and things like that, which will do things as quickly as possible. Here we do not know which rule will fire when essentially, I mean which instance of a rule which fire. So, it may end up doing a lot of unnecessary swapping, but eventually it will solve the problem, it will sort that array. So, if you have plenty of time, you want to start your machine and go off and go for a walk and come back, then maybe this is a good idea. So, let us look at the match again. A rule has a match with a working memory element, a match in the working memory with a working memory element, if each positive pattern has a matching working memory element. So, we have a rule, it is got pattern 1, pattern 2, pattern 3 and each pattern, each positive pattern must match some working memory element. Unsigned patterns are by default positive. And the second condition is that for every negative pattern, there must be no matching working memory element in the working memory. So, every positive pattern must match something and the negative pattern should not match something. A pattern in a rule matches a working memory element in the working memory if the class name of the pattern is the class name of the working memory element. So, these are constants in your expressions. So, they must match. So, if you remember the unification algorithm, it is kind of based on that essentially, except that you are not making them identical. You are saying that okay, this pattern must match certain criteria within the working memory element. So, it could be greater than 19 or something like that, all that is allowed, or it could be a disjunction, that is also allowed. So, the class names must match, of course, and the attribute condition in the pattern. So, notice that we are not saying the attribute value in the pattern, we are saying attribute condition in the pattern matches the attribute value in the working memory element. Working memory elements will have only values, but the pattern must match that value. So, if I have said greater than 19, then any value greater than 19 will match with that. Attributes that are not mentioned in the pattern, but are present in the working memory are just simply ignored essentially. So, we are not looking for, if supposing I am saying I am only looking for a student who got marks greater than 79, then I do not care when looking at the working memory element what is the name of the student, what is the age of the student and things like that. So, whatever I state in the rule is what I am looking for in the working memory element. Other attributes are ignored. So, this we have mentioned earlier. So, let us just look at it again. If the attribute in the rule is a constant, then it will only match an identical constant. That is like in unification. If the attribute is a variable, then it will match any constant. So, this it makes it like a, again like unification, that it will match any constant. But the other conditions are a little bit different. When we say equal to or not equal to or not same type as or same type as, then it will only match certain things essentially. So, I can do things like n equal to 3, n is a variable, remember. So, that is fine essentially. I can write this pattern in my rule, and if the value in the working memory element is 3, then this will match essentially. I can even say x equal to y essentially. No, this x may be in my first pattern in the rule, y may be in my second pattern in the rule, and in the third pattern I may say that value of x should be same as this value of y in the second pattern. So, that is also allowed. Same type as, we will not get into the same type as here. We can also do comparisons. We can say this value must be less than 3. We saw that when we were talking about ranking, or it must be x can be greater than or equal to y. All these things are allowed essentially. We can do conjunction, that we have already mentioned, that if there is a curly brackets with a set of tests, they do not have to be constant, they can be tests. So, for example, I might say the number must be greater than 25 and less than 43 essentially, then it would match essentially. Likewise, I can do a disjunction of tests, that the number must be let us say less than 30 or greater than 40, which means I am excluding all numbers between 30 and 40. So, anything would match. If I say less than 30 or greater than 40, that means 16 would match, 47 would match, but 35 would not match actually. So, in that sense it is quite powerful. So, let us say we are doing this swap sort and we are also doing this ranking, and let us say we have put all the rules together into one program, which is not always a good idea, but let us say we have these rules and we have this working memory element. So, we have a certain number of elements in that array, and we have a certain number of working memory elements describing marks of students. Then this match process is going to look for matching pattern. So, for every working memory element, it will, for every pattern in all the rules, it will try to see whether it matches or not. So, for example, this match would succeed, that the array index I value x would match the first working memory element. It will also match the second memory element, but that would be a different rule, essentially different instance of the rule. For one instance of the rule, the first pattern would match 1, the second pattern would match 3. Likewise, if I am looking at the other rule, the first pattern would match working memory number 5 and the second pattern would match the working memory number 7, and we assume that the third pattern does not match anywhere. If that happens, then we would have these two instances of the rules with these two these elements into the working memory, into the conflict set, and the conflict set would look something like this. It is a set which is made up of tuples, where each tuple starts with a rule name and the timestamp of the working memory that it is matching essentially. So, the two examples that we saw are shown here on the left. So, swap sort matches 1 and 3 as we saw, 1 here and 3 here. Ranking that rule, it matches 5 and 7. So, 5 is here and 7 is here. And of course, there are other things in the conflict set, but this is the general idea of how the conflict set is computed. Next, we want to talk of conflict resolution essentially. Supposing there is a whole set of rules which are matching. So, the following rule spots let us say 2 values which are out of place. That is a swap sort rule essentially, right. If there is a value at a later index which is smaller than the value at an earlier index, then you want to swap them. So, given a large set of working memories elements, which means given a large working memory, the rule may match many pairs of elements. So, let us say in the extreme example, when I have given you a array which is sorted in the descending order, then every pair of elements would match this rule essentially. You can see that all combinations would be kind of clamoring to get selected. That is what it means to be in a conflict set, that select me, that kind of stuff. The set of matching rules with data is called a conflict set that we have seen. The inference engine selects one rule from the conflict set and executes it. Now, this is a point that you can think about if you are going to implement a rule based system in the future sometime, that under what conditions. See, nowadays we have multi-threaded machines and you can do a lot of concurrency can be built into programs and parallelism can be built into programs. So, you can try to imagine the conditions under which all matching rules can be fired at the same time. That does not happen in OPS 5, but you can see that in certain domains it should work, but in certain domains it would create chaos, especially if you are let us say updating elements and let us say sorting a list, then there it would create chaos essentially. But for certain elements which are used for let us say just pattern classification or pattern recognition, you may spot different patterns and say, oh, this is there in the image, there is a horse in the image, there is a chair in the image and things like that. So, maybe they can be done in parallel. So, just give some thought to when can we allow the entire conflict set to be executed in parallel. What kind of applications would that be useful in? We will not get into that here. Conflict resolution is the task of choosing one rule and saying, okay, this is a rule that is going to get to execute next. Of all the rules that are saying execute, clamoring for attention, saying this rule is going to be executed next or fired next. And we will look at that, we will come back and see this again essentially.